Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on Zener diode and its VI characteristics. The Zener diode, or the breakdown diode as what it is commonly referred to as, is basically the same as any standard PN junction diode, but they are specifically designed to have a low and specified reverse breakdown voltage, which will take advantage of any reverse voltage applied to its terminals. The Zener diode allows current to flow in the forward direction in exactly the same manner as any PN junction diode. However, the difference comes when it is reverse biased. That is, the Zener diode also permits current flow in the reverse direction when the applied voltage is above a certain critical value known as the reverse breakdown voltage. American physicist Clarence Zener discovered this property, and hence this diode is named after him as Zener diode. Please note the schematic symbol and physical model of the Zener diode as what is shown in the figure 1 here. Let us now understand how this Zener diode works by applying it to a simple circuit. Figure 2 shows a simple Zener diode connected to an input voltage and a load. Let us now try to understand how reverse breakdown occurs in a Zener diode and what is the cause for it to occur. In Zener diode, the reverse breakdown occurs due to electron quantum tunneling under high electric field strength, and this mechanism is called Zener effect. In simple words, Zener diode breaks down due to the movement of free charge carriers in the diode due to the application of high electric field. When I say high electric field, you must note that it is nothing but high value of input voltage being applied. It must be noted that a Zener diode has a different doping concentration than a normal PN junction diode. A Zener diode is doped properly so that the breakdown voltage can be modified by controlling the depletion region width of the diode. This modification provides an advantage to using a Zener diode in reverse biased condition. Let us now talk about the different types of breakdowns that occur in a diode. As already mentioned, the Zener diode behaves like an ordinary signal diode when it is forward biased. However, Zener diodes are most often used in reverse biased conditions. We know that if the applied reverse potential is very high, a diode will go into breakdown, causing a rapid increase in the device current. We have already discussed this when I was discussing the working principle of a semiconductor diode, and you can watch that video as a prerequisite to this video by clicking on the link shown in the top right corner right now. Coming back to this discussion, let us now talk about the breakdowns itself. A diode can break down due to two types of effects. The first one is called the Zener conduction. The second one is called as avalanche. The Zener diode takes advantage of this reverse breakdown effect in order to produce a stable voltage across its terminals. In fact, Zener diodes are specified by their reverse potential, and these potentials are generally referred to as Zener voltage. Also, it must be noted that they are designed to handle larger currents and powers than any average signal diode. In practical world, Zener voltages are standardized in much the same manner as resistors, so values such as 3.9 volt or 5.1 volt or even 6.8 volt can be expected. Coming to the figure 2 here, please note the way in which the Zener diode is connected across the source. Assume that the voltage applied has such a polarity. Now, since the positive potential across the input voltage is connected to the cathode of Zener diode and negative potential to the anode of Zener diode, the Zener diode will be reverse biased. And depending upon the value of the input voltage, the Zener diode either will conduct or not conduct. If it conducts in the reverse biased mode, then there will be a finite amount of voltage drop across the same, and this is called as the Zener voltage. So, whatever the value of input voltage be, once the Zener diode breaks down and starts to conduct in reverse biased condition, the voltage across the load is exactly the same as the voltage across the terminals of the Zener diode. This particular principle of the Zener diode is most commonly used in voltage regulation techniques. Let us now talk a little bit on Zener voltage. Zener voltage is nothing but the voltage across the terminals of the diode, when it is under the reverse conduction mode. In simple modes, it is the voltage across the diode when the diode breaks down. In an interesting fact, you should note the Zener voltage is measured at a specified current value, which is called as the Zener test current, and it is denoted by IZT. We call this as the Zener test current. If the current through the device is less than the Zener test current, then the diode will not break down and the voltage across the diode will be less than its specified value. In simple words, the voltage across the diode, if the value of current across the Zener diode is less than IZT, will be less than the value of the Zener voltage specified to it. Generally, when a signal diode is reverse biased, we know that we treat it as an open switch. However, the same cannot be said about the Zener diode. This is because a Zener diode will start to conduct once the applied voltage is greater than the reverse breakdown voltage. In simple words, if the input applied voltage is greater than the reverse breakdown voltage of the diode, the Zener diode will start to conduct. Because of this behavior, a Zener diode can be treated as an open switch only when the applied voltage is lesser than the reverse breakdown voltage. So, if I denote the input voltage as Vin and the Zener reverse biased voltage as, let us say, VZRB, then if the value of Vin is less than value of VZRB, then the diode will not break down and therefore it acts as an open circuit. Once the applied input voltage becomes greater than the reverse breakdown voltage of the Zener diode starts to conduct, and now it can be modeled as an voltage source equal to the rated value. That is, if the value of Vin is greater than the value of the Zener reverse breakdown voltage, then the Zener diode now acts as an voltage source. Please note this particular characteristic of the Zener diode because this is one of the most important features of a Zener diode. Whenever the voltage across the input is greater than the reverse breakdown voltage of the diode will start to conduct, and instead of acting as a short circuit, now this acts as a voltage source, and the voltage across the Zener diode will be equal to the reverse breakdown voltage of the same. Therefore, whenever you are analyzing Zener based circuits, the first thing to do is to determine if the diode is forward biased or not. If it is forward biased, then you simply treat it like any other ordinary switching diode. If on the other hand it is reverse biased, then you need to check the voltage across the diode. If the voltage across the diode is lesser than its Zener voltage, then you have to treat it like an open switch. On the other hand, if the diode voltage is greater than its Zener voltage, then you need to recompute the circuit, but this time you have to mentally replace the Zener diode with a voltage source with a value equal to the Zener voltage. In simple words, when the Zener diode breaks down and starts conducting in the reverse biased mode, it has to be replaced as if it is a voltage source, and the value of that voltage source will be equal to the Zener voltage of the diode. Having had that brief introduction to the Zener diode, let us now discuss the VI characteristics of the Zener diode, and these are shown in the figure 3 here. You must note that when the Zener diode is forward biased, it acts as if it is nothing but a simple PN junction diode. It is actually the reverse biased mode which is more interesting here. So let us discuss a little bit more on that. Please note, when we were discussing the working principle of a PN junction diode, we learned that when the PN junction diode is reverse biased, the depletion layer will become wider. If this reverse biased voltage across the diode is further increased, the depletion region becomes more and more wider. At the same time, there will be a constant reverse saturation current due to the flow of minority charge carriers. After a certain reverse voltage across the junction, the minority charge carriers will get sufficient kinetic energy due to the application of high electric field, which is nothing but the input voltage. When this happens, free electrons with sufficient kinetic energy will collide with the ions in the depletion layer and thereby creating more free electrons. These newly created free electrons will also get sufficient kinetic energy due to the same high applied electric field, and they create more free electrons by cumulative collision. Due to this cumulative phenomenon, very soon a huge number of free electrons will get created in the depletion region. This will cause the diode to break down and then it will start to conduct. You must note that this type of breakdown in a diode, which is caused because of high kinetic energy of electrons, is called avalanche breakdown. Please note, we have not shown the avalanche breakdown in figure 3, but avalanche breakdown is being discussed as a prerequisite to Zener breakdown. So let us now discuss about the Zener breakdown. Zener breakdown is said to be sharper compared to avalanche breakdown, and this usually occurs only when the diode is doped with a certain amount of concentration. Please recall, a Zener diode is highly doped as compared to that of a regular p-n junction diode. This higher concentration of impurity atoms causes higher concentration of ions in the depletion layer. Therefore, for some applied reverse biased voltage, the width of the depletion layer in a Zener diode will be considerably thinner than that in a normally doped diode. Please note, a Zener diode is highly doped, and therefore, when I apply some voltage, the width of the depletion layer in a Zener diode will be smaller than that in a regular diode. Because of this thinner depletion layer, the electric field strength across the depletion layer will be quite high. If I now further increase the reverse voltage across the diode, then the ions in the depletion layer will start to come out, and soon the depletion layer will completely break down. When this happens, the Zener diode will start to conduct. This type of breakdown is called as Zener breakdown, and the voltage at which this breakdown occurs is called as Zener voltage. I am currently talking about this particular voltage, which is Zener voltage. Please note, if the applied reverse voltage across the Zener diode is more than the Zener voltage of the same, the diode will start to conduct and there is no chance of further avalanche breakdown in the same. So, when the applied reverse voltage becomes equal to the reverse breakdown voltage, the Zener breakdown will occur and there will be a sudden increase in the current as what is shown in this region of the curve. Once this reverse breakdown voltage is reached, the voltage across the diode is now equal to Vz, and this voltage remains constant even if you continue to increase the reverse applied voltage. So, in practice, we can say that Zener breakdown occurs at a lower voltage as compared to that of an avalanche breakdown, and this is mainly because Zener diodes are purposefully doped for the Zener breakdown. It should also be noted that the Zener voltage of the diode gets adjusted during manufacturing process with the help of a required level of doping. When a Zener diode is connected across a voltage source and the source voltage is more than the Zener voltage value, the voltage across the Zener diode remains fixed at Vz irrespective of the source voltage. However, at the same time, the current through the diode can be of any value depending upon the load connected with the diode. Let us come back to this and understand this point. So, what I am trying to now say is that when the Zener diode breaks down, the voltage across the Zener diode is fixed and that is equal to Vz. This is the Zener voltage of the diode. Therefore, irrespective of the amount of input voltage that is being applied, the load here will only see a voltage equal to Vz across the same. However, the current across the Zener diode can vary depending upon the value of the load that is connected to the circuit. This is one of the main reasons why we use Zener diode to control the voltage in different circuits. Let us now try to summarize what we have learnt about the Zener diode and its VI characteristics. When the Zener diode is forward biased, it acts as if any other signal diode. So, we understand that when the Zener diode is forward biased, it operates as a short circuit. On the other hand, when it is reverse biased, we have some important features to learn. Under reverse bias, we have to take two conditions. The first condition is when the value of the input voltage is less than the reverse breakdown voltage of the Zener diode, which is VZRB, then the Zener diode acts as if it is an open circuit. On the other hand, when the value of the input applied voltage is greater than the reverse breakdown voltage of the Zener diode, now the Zener diode operates as a voltage source, and the value of this voltage source is equal to the Zener voltage value of the same, which is commonly denoted as Vz. Once the Zener diode breaks down, even if I increase the value of input voltage to a large value, the voltage across the Zener diode will remain constant at the value of its rated Zener voltage, and it will not change. This particular characteristic of the Zener diode is used in voltage regulation techniques. Right, that is about a brief discussion on Zener diode and its VI characteristics. In my next video, I'll discuss Zener diode in the application of voltage regulation. So stay tuned. Well, with that, we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.